Streams and rivers are often referred to as the lifeblood of the land. Few places make this more apparent than the arid and semi-arid portions of the western U.S. For a brief period that may only last a few weeks a year, there is enough water for life to flourish here, turning vast expanses of rangeland into a sea of green. During the remaining time, streams and their riparian areas are the primary source of water, emerald green lines in a land that is dominated by browns and yellows. The dense vegetation of riparian areas helps to trap sediment and pollution that is transported by overland flows during rain and snowmelt. This decreases soil erosion and helps to improve water quality. During high flow events, the vegetation helps to slow water that escapes the stream banks. This water can then deposit its excess sediment and nutrients while some of it infiltrates into the soil. This allows riparian areas to act as a sponge, absorbing water during wetter conditions, then slowly releasing it back into the stream as conditions dry. The water and nutrients that are absorbed promote the growth of denser, more luxuriant vegetation like that seen in the photo on the left. The photo on the right shows just how severe the contrast between dry, sparsely vegetated uplands and wetter riparian areas can be. Slowing stream flow and encouraging the movement of water into the soil can lessen the energy of the stream. The dense riparian vegetation can help trap debris that would otherwise clog road culverts and irrigation structures downstream. You can see in the picture on the right that downed trees and branches were caught in the riparian area during a past high water event. By doing this, riparian areas can help to reduce downstream damage from flooding. Despite making up less than 2% of the western landscape, riparian areas can account for up to 20% of available forage, and in some areas as much as 80% of forage consumed by cattle. The allure of riparian areas goes beyond just supplying more abundant vegetation and water, however. Taller grasses and woody vegetation that grow in many riparian areas can also provide protection from the sun during the heat of the summer and shelter from the wind and blowing snow during winter. Of course, livestock producers aren't the only ones that benefit from riparian areas. In arid and semi-arid regions, up to 80% of wildlife species also rely on riparian habitat at some point during their lives. The vegetation here is especially attractive to insects and arachnids, and for pollinator species, riparian areas can represent one of the earliest and longest-lasting sources of food. The abundance of food and shelter also draws species that are typically associated with upland habitat, such as sage grouse and pheasants. For sage grouse, proximity to riparian habitat is a significant predictor of breeding sites and is often crucial to the survival of their young. In addition to the benefits of food, water, and shelter, riparian habitat also serves as a corridor for wildlife travel. From tiny insects and rodents to elk and moose, riparian corridors provide habitat connectivity for species that would otherwise find themselves restricted to isolated pockets. These benefits to wildlife can also benefit landowners. Areas managed with wildlife in mind can be used for the recreational enjoyment of family and friends, or be utilized to diversify income through fishing and hunting opportunities or through agro and ecotourism. The demands placed on streams and riparian areas have had their effect, though. Historical land use, changes in precipitation regimes, and prolonged drought have caused many streams to become degraded. This is a seasonal creek on public land in northwestern South Dakota. You can see the results of natural salt deposits combined with the changes to water management and land use within the watershed. Repeated wetting and drying has caused salt to leach upwards and migrate into the riparian area with water as it flows from the uplands. The heavy accumulation of salt has led to a shift in the vegetation community, which was compounded by heavy trampling from cattle. You can see how sparsely vegetated the floodplain is, with many of the remaining plants being either distasteful or poisonous to both livestock and wildlife. This picture is located just a few hundred meters downstream, where the lack of vegetation and structure have allowed the creek to dig into its own bed. The incision here is so bad that riparian vegetation can only exist for a meter or two around the pool before water becomes too difficult to reach. You can see that the salt is beginning to accumulate here as well, and that trampling by cattle trying to reach the pool to drink is causing the incision to spread. Streams like this are common throughout the northern plains. Traditional restoration to repair damage like this is often costly, invasive, and heavily regulated, which makes it prohibitive for many landowners whose time and money are limited. This has led to an interest in alternative restoration methods that can be effectively used by private landowners and small groups while still being able to be scaled up to larger restoration efforts. Among the most popular restoration methods that arose are what are referred to as process-based restoration. These methods rely on natural stream processes rather than forcing streams into a desired state that may or may not be sustainable. These methods are varied and are based on the work of many different practitioners in a multitude of settings. South Dakota State University, the Nature Conservancy, and the NRCS set out to find process-based restoration methods that were cheaper than traditional methods, minimally invasive, and which could be used by private landowners with minimal expertise and permitting. Collectively, we refer to these as low-cost, low-tech tools. Part of this research looks at channel-spanning structures such as beaver dam analogs and post-assisted log structures, or BDAs and PALs for short. We believe that these structures could have significant effects on the soil moisture, forage production, and plant community structures of riparian areas in the northern plains, and that they could be used to the advantage of livestock production. BDAs and PALs are simple structures built from local materials such as downed tree limbs, live cuttings from riparian species, sod mats, and rock. Depending on the site, untreated posts are often used to anchor the structures in place, though some projects may be able to use local materials for posts as well, or do without posts altogether. These structures are not permanent and generally only last a few years before needing repairs or replacement. During planting, sites that offer additional anchor points such as larger downed trees, boulders, or root wads on the stream bank are often chosen for structures in order to increase their durability. To further improve their effectiveness, multiple structures are placed so that the effects of the structures becomes cumulative, and the failure of any single structure is unlikely to cause a failure of the restoration as a whole. In 2022, 4 sites were selected from headwater to medium-sized streams in the 60A and 63A major land resource areas to maintain a degree of similarity in the ecology, geology, and topography of our sites. Among our sites was the lower reaches of Cottonwood Creek on the South Dakota State University Cottonwood Field Station near Phillips, South Dakota. The Cottonwood Research Station is a roughly 2,500-acre active cattle-producing operation where SDSU researchers and students perform applied research into animal nutrition, grazing management, rangeland ecology, and riparian restoration. There are almost 6 kilometers of Cottonwood Creek on the research station. Despite being a mid-sized prairie stream that drains hundreds of square kilometers, Cottonwood Creek is ephemeral. Most of the creek on the station is incised from 1 to 3 meters, and it is completely disconnected from its historical floodplain during all but the worst flooding. Further complicating matters, 2 segments of the creek were straightened at an unknown time in the past. This led to increased flow velocity and erosion during high water and has made the areas downstream even more unstable. Inset floodplains have formed in many parts of the creek, but its flashing ephemeral flows mean that most of them only last for a few years before being scoured away. Because of this, the inset floodplain has few trees or shrubs. Historically, there was a beaver population here, but they were not active on all parts of the creek during most years. They were trapped out entirely in 2019 to facilitate cattle production. Beavers remained on the properties up and downstream, but were only transient within the station. The site that we selected on Cottonwood Creek was located on the downstream end of the station. The site was broken into 6 experimental reaches, 3 each of control and treatment. Each reach was a little over 70 meters long, or roughly the equivalent of 20 bank-full stream widths. The control reaches were located on the southern, upstream portion of the site, and were separated from the treatment reaches by 2 reach equivalents to minimize the effects between reach types. Within the control and treatment sections of the site, individual reaches were separated by at least 1 reach equivalent. Like most of the creek on the station, this section didn't flow during most of the summer, though there was often water in the last 200 to 300 meters. Despite signs of beaver on nearby properties, signs indicated that it had been several years since they had been present here. Because of the nearby beavers and the severity of stream incision here, which would require long-term maintenance, reassessment, and construction of new BDAs and PALs to fully treat, it was decided that the primary goal for this site was to bring back the beavers and let them do the work for us. Unfortunately, despite signs of nearby activity, the nearest known active dam was kilometers away, and the beavers' preferred food sources were located on the terrace of the stream, which was over 2 meters up a steep bank in most of this area. Because of this, we anticipated it would take a few years for them to return. This was the nearest beaver dam known to be frequented by beavers. It was separated from our test site by over 3 kilometers of stream. When we looked at this dam during site selection in spring of 2022, it was over 2 meters tall on the downstream side and almost completely impermeable to water. According to the station staff, it had been there for years, and all efforts to remove it by hand had been abandoned. We believe that this dam, which was constructed largely of clay from the stream bed and banks, had dried out as water levels in the creek dropped, causing it to lose much of its structural integrity. On August 26th, about a month after our structures were built, a storm dropped 20 millimeters of rain in a day. The picture on the left shows what was left of the dam shortly after this rainfall. It appeared that the sudden influx of water had caused it to fail completely in a matter of seconds. Mud deposits and vegetation left downstream showed that the resulting surge of water peaked at almost 2 meters above the previous water level, even 3 kilometers downstream. A search of the creek a few months later found the remains of an old beaver dam that are shown in the picture on the right. This area had no signs of beaver activity in recent years, and the creek here had not been examined during site selection. If this dam was still standing, but in a state of disrepair when the other dam breached, it would have only added to the damage downstream when it too failed. The flood destroyed or severely damaged over half of the structures that we built. This was the largest structure that we created on Cottonwood Creek, and the one furthest upstream that was left intact after the flood. It was anchored into the upstream side of a downed cottonwood in order to reinforce it. For reference, the top of the cottonwood log is a little less than 2 meters above the stream bed. You can see how much debris it collected during the flood. Downed branches, fence posts, and the shattered remains of the structures from upstream all came to rest here. The original structure is no longer visible, and the accumulated material has almost doubled its height. This structure served its purpose better than we could have ever anticipated, slowing water so that the 4 structures downstream also survived intact, and backing water so that the structure immediately upstream was only slightly damaged during the initial flood surge. It also allowed something that we hadn't anticipated, at least not for a few years. Within a few days, new beaver sign was seen in the area for the first time since beavers had been trapped out. Newly cut and gnawed trees were found, even in areas where the creek was deeply incised. Just a few meters downstream from our first experimental reach, a roughly 70-centimeter tall dam now spanned the creek. The effects of this single dam exemplify what we sought to mimic with our BDAs and PALs. Before our structures were installed in July, you can see just how low the water in the creek was, despite having over 70 millimeters of rain in the previous month. By mid-August, dry conditions and a lack of return flow had lowered creek levels to the point that Cottonwood Creek no longer flowed. Any remaining water was in a series of disconnected pools that were rapidly shrinking in the summer heat. You can see our structure in this image, but by the time this was taken, there was almost no water left upstream of it. Then the storm on August 26th happened. You can see where the beavers built their new dam and formed a pond. With the low stream gradients on Cottonwood Creek, this one dam backed water for over 200 meters. Not only did the new beaver dam slow the water and cause it to back up, unlike the beaver dam that had breached, this dam was still permeable to water. You can see in this video how the water level below the dam is almost equal to the pond above it. Recolonization or reintroduction of beavers is one of the major goals for many restorations utilizing BDAs and PALs. It was the primary objective for the Cottonwood Creek site, but because of the severity of the stream incision and lack of woody vegetation throughout the inset floodplain, it was expected to take 2 or 3 years for beavers to return. Thanks to an unexpected disaster, we achieved this goal in a little over a month. As is often the case, it was humans who had to adjust to fit new realities imposed by nature. The recolonization of one of our experimental reaches by beavers has required adjustment to the original plan for this site. Because of the significant effects beavers can have on vegetation and stream morphology that BDAs and PALs do not, this site can no longer be treated as equivalent to the other sites in the study. Instead, the Cottonwood site is now being treated independently of the other sites and will be integrated into future projects researching other aspects of restoration utilizing BDAs, PALs, and beavers. Riparian areas are a key part of the western landscape. They are crucial to livestock and wildlife that depend on them for survival during part or all of the year. They act as a sponge that can absorb and store water, and in doing so can help to mitigate the effects of fire, flooding, and drought. Unfortunately, historic land management practices and changing water regimes have degraded many streams throughout the world. Low-cost, low-tech tools such as beaver dam analogs and post-assisted log structures rely on natural stream processes to restore riparian areas and reconnect floodplains. They are becoming increasingly popular due to their relative ease of construction and the ability to implement them at a variety of scales. These structures have been shown to have positive effects on stream and riparian health in several areas of the western U.S., but have only recently been tested in the northern plains. Despite their temporary nature, these structures can continue to improve stream and riparian habitat even after the structure has technically failed. In the case of Cottonwood Creek, despite losing half of our structures, BDAs and PALs encouraged beavers to recolonize a portion of the stream that they had been absent from for years, turning what was otherwise a disaster into an opportunity. We would like to thank our project partners at the Nature Conservancy and NRCS. Special thanks to Lori Brown with the Nature Conservancy and Mitch Faulkner with the NRCS Belle-Fourche office. Primary funding for this research was provided through the North Central SARE program. Partial funding was provided by the Nature Conservancy through the Nebraska chapter's J.E. Weaver Competitive Grant Program.